Current President, and it's my pleasure to welcome you and to introduce the key players this evening and chair the meeting. The Royal Society of Edinburgh is Scotland's national academy. We have about 1,600 fellows, top academics in science, arts, humanities, social sciences, leaders of professions, business, civic leaders, practicing artists, leaders of all sorts in Scotland. We aim to contribute to the social, cultural and economic well-being of Scotland through, in the terms of our charter, the advancement of learning and useful knowledge. Before the main lecture, I have the honour of presenting the Early Career Prize, the Sir Thomas MacDougall Brisbane Medal, and it's being presented, get the right sheet of paper, being presented to Dr. Malcolm MacDonald, Reader of Space Technology, Department of Mechanical Aerospace Engineering at the University of Strathclyde. It's for his outstanding research in the development and application of space mission systems to challenge conventional ideas and advance new concepts in the exploration and exploitation of space. Besides being this year's medal winner, Dr. MacDonald is also a member of the Royal Society of Edinburgh's Young Academy of Scotland. So can I ask Dr. MacDonald to come forward to receive his medal? Many congratulations. We then move on to the presentation of the senior prize, the Lord Kelvin Prize, to Professor Anthony Doyle, and he'll be shortly giving us the lecture as well. Find the citation. Sorry. So this goes to Professor Anthony Doyle, Fellow of the Royal Society of Edinburgh, Professor of Physics, School of Physics and Astronomy at the University of Glasgow, for his outstanding contribution to the field of experimental particle physics and for his extensive public engagement activities. Through developing critical analysis methods, his work has led to major developments that have made the recent discovery of the Higgs boson possible. So, Professor Doyle. So we're now going to hear in a moment or two from Professor Doyle, and I'll give you his title and so on in a moment. Sorry, I've got too many pages of brief. So Professor Doyle's Professor of Physics and a research group leader of the Particle Physics Experimental Group at the University of Glasgow. As an STFC Senior Research Fellow, a CERN Associate, and a member of the Atlas collaboration, he's been working on analysis methods to search for and discover the Higgs boson at the Large Hadron Collider near Geneva. He was chairman of the Atlas Publications Committee in 2012 when the Higgs boson was discovered. He's a fellow of the Alexander von Humboldt Foundation, the Institute of Physics, and, as I've already said, the Royal Society of Edinburgh. And his lecture is entitled From the Infinite to the Infinitesimal, Birth of a Higgs Boson. Professor Doyle.
So thanks very much. So I'm Tony Doyle. I'm going to give you two talks, actually. So the first one is From the Infinite to the Infinitesimal, and the second is Birth of a Higgs Boson. And the idea here was that there was a kind of tale of two talks. So I started with one which was on the left-hand side. This was an inspiration from Peter Higgs. So Peter wrote lots of talks a few years ago, and they tended to be titled My Life as a Boson. He was inspired by a Swedish film at the time, which was My Life as a Dog. And in honour of that, we named our dog Higgs. So that's a picture of Higgs, our dog. So one is more theoretical. So the infinite to the infinitesimal is meant to try to get this association between the very large scale of things and the very small scale of things, which I do from day to day. And then the birth of the Higgs boson will be more to do with experimentally what do we do at the LHC. So I hope there's enough time to go through both aspects. So any good story should start with a few points. So the first part of the story is all about from the multiverse of infinitesimal probabilities, our universe emerged. And there are 10 points I wanted to lead you through. So first was at the instant of the Big Bang, the universe was comprised of particles of pure energy. And then approximately a microsecond later, the universe cooled sufficiently that a Higgs field developed. The particles then began to acquire mass as they moved through this newly created Higgs field. And the particles lost kinetic energy, they gained mass through E equals mc squared. The elementary particles developed and the Higgs field continued to permeate space-time. And in unification theory, physicists looked to the Big Bang for evidence of a single superforce at the start of all these things. So each of the four fundamental forces is thought of as a manifestation of a single force. So 380,000 years later, the universe cooled sufficiently to form atoms emitting light. And then 13.8 billion years later, that finds us here now, we're bathed in this cooled light, the microwave background. And now particle accelerators are recreating the earliest conditions after the Big Bang. So 1/10 billionth of a second after the Big Bang is the point at which we're looking at the LHC. So I'm not sure whether Lord Kelvin would be too happy with this. He spoke about when you can measure what you are speaking about and express it in numbers, you know something about it. So there aren't so many numbers on that slide, so let's see if we can get a bit further in terms of numbers. Okay, so first let's set up a few puzzles to do with our universe as it exists. So the first puzzle we have is that there's dark matter in our universe. So the way that was first observed was that galaxies and clusters of galaxies rotate too fast. So if you see here on this slide, there's an expected curve. If the matter followed the visible things that we see, the stars and so on, then you would expect a rotation curve which looks like the one pointed at by the red line. But the actual data preserves it goes out longer distances. And so there's something else which is managing to rotate both those galaxies and those clusters of galaxies far faster than you might expect. So that's one puzzle. The second puzzle is dark energy. So we know that the universe is expanding, and we've known that for a long time from Hubble, 1929. So this was his data, and this was the receding velocities, and hopefully you can draw a straight line through those dots, although experimentally you might be challenged to do so these days. But that's the data he used and was able to show that the recession from a Big Bang. And now what we see is that as you get more and more improved data, as you go further and further out, then there's actually a deviation from that straight line. So the universe is not just expanding at some uniform velocity. As you go out to the very furthest edges, it's actually accelerating away. And we don't know much about what the mechanism is by which that acceleration occurs. And so we refer to that as dark energy. So puzzle 2 is dark energy. And so the combined puzzle 3 is the composition of the universe. So fundamentally, we don't know what 95% of the universe is made of. So we know an awful lot about matter, and we know how that distributes itself, and we know all of the sort of theoretical ways in which the matter particles combine and so on. But we know essentially nothing about dark matter or dark energy. And to give us clues as to how to proceed to understand this in the longer term, we have 3 equations. So the first one is E equals mc squared. So Many of the questions that we're asking about involve hypothetical particles, and we want to investigate those. So from Einstein's E equals mc squared, we know that energy can be transformed into mass. So essentially at the LHC and elsewhere, you can make new heavy particles, provided you can smash them together at some high energy. And the basic unit of energy here is the electron volt, and that corresponds to the energy that a single electron would receive when powered by a battery as it goes through a loop. So that's the starting point. Then second, we know that there's available thermal energy in this expanding universe. So there's another relationship, which is that from Boltzmann, that energy is proportional to temperature. And that proportionality constant is just K. And the universe just after the Big Bang was very small and very hot. At the sort of distance scales that the LHC probes, it was 10 to the 15 Kelvin. And we can now go back this 13.8 billion years. So that's the second equation there. And then the third equation is one which relates the distances which we can probe with that high energy. So as you go up to high energies, then from the Planck relationship, which relates wavelengths to momentum, there's an inverse relationship there. And from the Heisenberg relationship, which relates momentum and time, then you can show that the energies that you're probing, at the very large energies that you're probing, probe very small distance scales. So energies that you can measure at the LHC, giga-electron volts at the LHC, can be translated into distances which are of the order of Fermi. So a Fermi is 10 to the minus 15 meters or so. So the idea is that as you get bigger and bigger microscopes, then you can see to higher and higher resolutions. So that sets the background to this. So the first part was about from the infinite to the infinitesimal. So the first thing we want to do is to sort of draw our ruler. Now this ruler is a bit different from the ruler that we would ordinarily draw. So this is a centimeter rule as normal, but it's now on a logarithmic scale, and it tries to encompass everything from the very smallest scales right back to the Big Bang up to the very largest scales, the scale of the known universe. So all things that we know of are on this scale. So we start here from the sort of human scale. So here's a typical human, perhaps not so typical, but anyway, one that might have something to say about understanding this stuff. And then on the very large end, we have the galaxies and all of that, and we probe there with things like the Hubble Space Telescope, which people will have heard of, but also lots and lots of other telescopes. So here's the antimatter spectrometer, for example, the Very Large Telescope, and so on. And then at the very small scale, you try to probe into matter, so you go below the level of the molecule, inside the atoms. Inside the atoms, there's the electrons which are orbiting the nuclei. The nuclei are composed of protons and neutrons, and inside those protons and neutrons are quarks held together by gluons. So that's the thing that we're probing at the LHC, and you can think about that as being a super microscope. So that's what happens in Geneva, and what we're studying are the physics laws of the first moments after the Big Bang, and there's an increasing symbiosis between particle physics, astrophysics, and cosmology. So let's go into that in a bit more detail. So on the infinite scale, so we all know about the solar system at the scale of 10 to the 12 meters or so. Then beyond our solar system, we're in the Milky Way, the galaxy, on the scale of 10 to the 20 meters or so. And the galaxies themselves are arranged in clusters, so they're also gravitationally attracted. So you get galactic superclusters. And then on the very large scale, the universe looks relatively uniform. So at the very largest distances we can probe, the universe looks quite uniform. Although if you look very closely, there are actually very small changes in the microwave density, that background light that I was talking about. And we now have this sort of precision which allows one to look at those very minute fluctuations in the early universe. So these all originate from very early quantum fluctuations, now expanded up to 10 to the 26 meters or so. So that's the very large scale of things. And then the infinitesimal scale of things is that we want to look inside the atom, inside the nucleus, inside the proton and neutron, and look into the world of quarks. So that's on this scale, which goes down from an angstrom, 10 to the minus 10 meters, down to a Fermi, 10 to the minus 15 meters, and below. And so the way that we do that is to go to the Large Hadron Collider, and it's one of the largest and truly global scientific projects ever. It's an exciting turning point in particle physics in terms of discovering the Higgs boson, but we're hoping that more can be discovered. And there are actually 4 collision points around the LHC and 4 detectors which accumulate data as particles come into collision. And we'll discuss that in the second part of the talk. So the idea is that we're exploring a new energy frontier with protons colliding on protons, and for a small period of time near Christmas, we also have heavy ion collisions at energies up to 14 TeV. And the key questions that we're asking are first about the origin of mass, and so that relates to Peter's Higgs mechanism, and that's a scalar field. We also ask about the unification of forces, and that involves symmetries and running coupling constants, and I'll try to touch upon that. And then we try to relate that back to the origin of the universe. So in the very early universe, very early on, the universe expanded very, very rapidly, and that corresponds to something called an inflaton. And there's a question about whether is that a scalar field like the Higgs boson. And then we talked about dark matter and dark energy, and again we can ask the question as to whether or not these are also scalar fields. But first let's take things back to the sizes of everyday things. So let's first of all understand the everyday physics that we have and try and use exactly the same tools to understand everyday physics that we then extrapolate up to these large and very small scales. So our universe provides us with 2 natural scales. They're the speed of light. So in conventional units, that would be 3 times 10 to the 8 meters per second. But in natural units, that would we just set c equals to 1. And then the other end of this, so that might be well known, the speed of light. But at the other end, on the very small scales, there's Planck's constant, which is the scale which relates energy to frequency, energy and time, and also momentum and distance. And again, we can set h bar equals 1 in trying to set sort of natural scales associated with these 2 fundamental constants. And the good thing when we set h bar equals c equals 1 is that interaction strengths become dimensionless. So what do I mean by that? So if we look at the energies of everyday things, so the first thing you might think of would be the binding energy of a hydrogen atom. So that's given by a quite complex formula there. It's 13.6 electron volts. And that's fundamentally the origin of the microwave background. Now, that's actually just the strength of the electromagnetic interaction which is governing that. And the electromagnetic interaction, when you set h bar equals c, is just 1 over 137. It's just a pure number. So you can rewrite this energy as just minus a half times this alpha squared times the mass of the electron which is orbiting the atom, times c squared. So that binding energy is just determined by the strength of the interaction, alpha, and an energy or a mass scale, me times c squared. And then h bar and c supply 2 of the 3 numbers to define our mass, length, and time scale. And then the third scale in this case is given by the mass of the electron. So that shows that there's a third important factor in terms of understanding our universe. So first there's Planck's constant, then there's the speed of light, and now there's a mass scale. So there are 3 dimensions of physics, if you like, h bar, c, and m. And what we'll be probing are the the energy scales associated with those masses. So that's the energy scales. We can also, we said there was a direct relationship between the energy scale and the distance scale. And so you can also ask about, well, why is the hydrogen atom the size that it is? Why is it approximately an angstrom or so? And that again, that's given by the Bohr radius, which again is just given by these constants. So the Bohr radius is just 1 upon alpha times this h bar c divided by MEC squared. So the size of the atom is governed by those fundamental constants. That's at about 10 to the minus 10 meters. Then the size of the nucleus is governed by, in a liquid drop model, it's just nucleons sticking together in this picture of the nucleus. And the size of the nucleons inside the nucleus, that's governed by the strength of the force binding the quarks and the gluons inside the protons and the neutrons. So that's given by lambda QCD, which has this particular value at these energies. So what we try to do when we go to the LHC is to create energies which go way beyond these kinds of energies. We want to excite new massive particles, and these may have energies which go up to giga-electron volts. So we might start to probe distances which are far less than 1/1000th of a Fermi, so far less than 1/1000th of the size of each individual proton and neutron inside the nucleus. And hopefully that enables us to discover new particles. So that's essentially why we were driven to build this very large Hadron Collider. And in fact, this h bar c and m allows you to look at all aspects of physics. So you might start from Newtonian mechanics at very small scales. In particle physics, we're governed by quantum field theory. So as you go down to very small scales and very large speeds, then quantum field theory plays a part. But there are all sorts of aspects of physics which are fundamentally all governed by the sizes of these things in terms of h bar c and m. So those are the three parts of that. And then the fourth part that we mentioned was this number, this 1/137. So Frank Close, who's quite famous on these subjects, so he says, alpha sets the scale of nature, the size of atoms and all things made of them, the intensity of colors of light, the strength of magnetism, and the metabolic rate of life itself. It controls everything that we see. So in 137, apparently science had found nature's pin code. So that's at one level. But then actually the reveal is that number itself, as we go across these vast distance and energy scales, in fact, that changes. So you find that as you probe very large energies, then the strength of this coupling constant, constant in brackets, or in parentheses, sorry, that constant actually varies, it runs. So we have to understand the nature of the vacuum in which we sit in order to understand why that happens. So we'll need the standard model at some point to understand that. So going back to the very large scale then, we talked about the sort of smaller scale things. So on the large scale, then we talk about the Big Bang, we talk about a rapid period of inflation, and then the first time scale we get to is that of 10 to the minus 10 seconds after the Big Bang, and the physics at the LHC corresponds to the conditions around that point. So that's the 10 to the 15 Kelvin in terms of temperature, or energies of around 100 GeV or so. And then the second interesting point is when the universe cooled sufficiently that electrons and protons could form. So that could happen around about 3 times 10 to the 5 years, or 3,000 degrees in temperature, or at energies of 3 times 10 to the minus 10 giga-electron volts in these units. So those are two interesting scales, and we'll try to talk about those next. So you can think about those two being the key Big Bang probes. So the physics of the LHC probes a very different scale to that of the microwave background, but both give you information about what's going on. So the physics of the LHC, so the time's around 10 to the minus 10, temperature 10 to the 15 Kelvin, energy is around 100 GeV. The universe was radiation dominated at that point and opaque. The microwave background is 380,000 years later. Still a small timescale on the scale of 13.8 billion years, but somewhat later. Temperatures are 3,000 Kelvin, rather lower, but still far higher than we would conceive of. And then energies of 0.3 electron volts, matter dominated, and suddenly the universe becomes visible at that point. And so we can look at this dark matter and dark energy as that evolves in this story. So although we talked about the composition of dark matter and dark energy as we exist now, back in the early universe, the proportions of those things were rather different. So today we have 1 hydrogen atom per centimeter cubed, but we also have 5 times that in so-called cold dark matter and 14 times that in dark energy. So the matter and energy content of the universe has also evolved with time. And the idea there is that there was an early phase where we're dominated by radiation. Then there's a matter era. And then finally, as we get to 1 on this, yeah, I can see. So 1 is where we are now. And 1, you see that dark energy now dominates at this point in time. And at least here in this simplest cosmological model is seen as a constant. So astronomers say that most of the matter in the universe today is invisible, dark matter and dark energy. And we can ask the question, is dark matter a supersymmetric particle? Is dark energy detectable? And we can look for them with the LHC. So that's the connection between these things. So what are these things that we look for in particle physics? So the fundamental particles as we know them today are these. So there's the so-called matter particles. They consist of the quarks inside the proton and the neutron. And the leptons, so the electron and its partner, the neutrino. And nature has this way of things that it actually replicates itself 3 times. So as well as the up and down quarks, there's charm and strangeness, top and bottom. And we don't know why, but nature has replicated itself 3 times on different mass scales for some reason. And similarly, the same thing has happened with the leptons. So there are 3 families of leptons, and we don't know why. And then there are forces. So we know about the electromagnetic force, which is governed by the photon, and the weak force, which is governed by the W and the Z boson. And we also know about the gluons, which hold together the proton and the neutron. So they bind the quarks together. So that's 3 forces there. So the electromagnetic force, the strong force, and the weak force. And at the moment, we have quantum field theories for those things. So we understand them at a sort of fundamental level. And the one that we perhaps know most about in terms of forces on a very large scale is gravity. But we still don't have a method to encompass that within quantum field theory. So that's, at the moment, a mystery. And sitting behind all of this, so all this replication of mass scales and so on, behind all of that, there's the Higgs field, which enables us to have a quantum field theory which can be self-consistently understood with these masses. So that's what the Higgs mechanism does for us. It allows us to consistently understand things at the very smallest level, incorporating all of the various masses which go into the standard model. So here, just to illustrate that, here are now the elementary particle masses, just illustrated with the mass being proportional to the area on this diagram. So the leptons are over on the left-hand top corner. So there's the neutrinos are almost massless. There's the electron, which is very small in mass. And then there's the increasing masses as we go up from the up and down quarks up to the top quark. And the photons and gluons are massless. We have the W and the Z bosons, which are massive. And now we've discovered the Higgs boson, and we find that the Higgs boson sits at essentially the same scale as the W and the Z bosons or the top quark. And that's very interesting from a theoretical point of view, why those sit together at that precise mass point, which a priori there are sort of an infinite scale of masses that one could choose, but this is the so-called electroweak mass scale. Okay, so that's about matter. That's probably what we know most about. Second, we know quite a lot about the forces by which they interact with each other. So we said we know something about electromagnetism, and we know from Maxwell that we can unify electricity and magnetism. And the idea is that beyond unifying electricity and magnetism, one can also unify electromagnetism and the weak scale. So we come up with an Electroweak formula. And the reason that the weak force appears weak is simply because it involves those massive bosons. The W and the Z bosons have mass, whereas the photon has zero mass. So that's a fundamental, initially lost symmetry, but now revealed symmetry, that the electromagnetic strength and the weak strength are essentially the same. And we might extrapolate beyond that and say, is there a way in which the strong force, as it runs in energy, may that ultimately unify? So there are certainly theorists who are looking at that idea of grand unification. So that is one preoccupation of theory at this point in time. And the idea is that these initially seen as coupling constants are actually running with energy. So the force actually changes strength very slowly, logarithmically with energy, but it does change strength. And an effect due to shielding initially from fermions, so matter loops, and also anti-shielding from boson loops, so the force loops as well. They lead to variations in this force strength with energy. So these numbers change with energy. So you have to keep track of those things. And so that's all done. And the slopes of these strengths, so this is 1 over the strength, and you plot 1 over the strength simply because then you get straight lines. And the slopes of those depend upon the content of the vacuum at the energy that you're probing. And you may or may not be able to unify these forces as you go up in scale. So that may require some extra theoretical ideas associated with something called supersymmetry. And so to get onto that idea of supersymmetry, so we can think about quantum numbers. And quantum numbers essentially are guided by symmetries. So this is a simple symmetry here in this picture of Stephen Hawking and Peter Higgs. This would be looking in a mirror, you see this thing. But you can distinguish between these two photos. So that is an example of parity being broken. So parity is an example of a quantum number. And there are fundamental quantum numbers, lots of them, at a very fundamental level. And it's actually those symmetries and the ways in which they break which determine the nature of the vacuum at a given energy. So when you can create new matter as you go up in energy, then you find that the forces can change their strength. So this depends upon, going up to higher energies depends upon various thresholds associated with the masses of new particles as they're created. And how do we go about creating those massive particles? Well, it's through the Higgs mechanism. So the idea here is that you draw a potential. So usually potentials would have a minimum at 0. But in the Higgs mechanism, the idea was that the potential 0 was offset from that where you would ordinarily expect the minimum to be. And that offset leads to a massive Higgs boson, but also leads to the ability of this Higgs field associated with this particle oscillating about at the bottom of this Higgs potential to interact with all the other particles and generate their mass. So we had some clues, in fact, from before the LHC, the Large Hadron Collider. We knew from quantum fluctuations of earlier experiments, even though we couldn't reach the energies which were needed to find the Higgs boson, we could predict the new matter before it was observed by very precise measurements which were guided by these vacuum fluctuations. So on the left, there's as a function of year, you can see how we homed in on the mass of the top quark through these virtual loops of particles here. So this represents here, this is the creation of a top anti-top virtual particle. And as we got more and more precise experiments, we could pin down where the top was. And then finally, we discovered it when we got to sufficiently large energies. Similarly, for the Higgs boson, we eventually could home in on where we had to search at the Large Hadron Collider. So the idea is that the primary objective of the LHC was to find this origin of mass. So is it the Higgs particle? So massless particles, we know, travel at the speed of light. A low mass particle would interact quite weakly with the Higgs boson. So that's the illustration there with just a few Higgs bosons hanging on, but can travel. It travels a bit slower than a massless particle, but not so slow. And then a really massive particle will travel slower still because it interacts more with the Higgs field. And the LHC idea was that with sufficient energy, you should be able to make a free Higgs particle and see that Higgs particle decay. So that's the second part of the story then, is this birth of a Higgs boson. And so this is a picture of Peter as an engineer. I'm sure with his hard hat on and doing all the right things down at the Atlas experiment. So Kelvin also had things to say about this. He said that when you're face-to-face with a difficulty, you're up against a discovery. In this case, he was right. So, but there was a lot of engineering which was involved in trying to manifest the Higgs boson in reality. So to create, it looks like a simple thing to just create this free Higgs boson from this picture, but of course an awful lot of engineering and developments were required. So I'll try to talk about some of the technical challenges to create the Higgs boson. So just as we talked about going from the infinite to the infinitesimal, here we can talk about the multitude of actually very small technical challenges that we had in experimental terms. And here were the steps which were needed in some ways. So first we had the Large Hadron Collider. That's a synchrotron ring which is powered by radio frequency cavities contained in a magnetic field, so you can accelerate particles to higher and higher energies. The Atlas and CMS detectors take snapshots of collisions inside the LHC every 25 nanoseconds, so that's incredibly rapid. And then only 1 in 10 billion of those events where the protons and protons collide is due to the Higgs boson. So you need an enormous amount of computing. So you have a worldwide grid of computers and storage that's used to analyze interesting events. And from a historical perspective, these technical developments took more than 20 years. And then on July 4th, 2012, that was our Big Bang moment with first evidence of the Higgs boson. And that required careful analysis of three decay channels, which enabled the discovery to be made. Run 1 of the LHC was over 3 years and culminated in 2013. And it focused on establishing the properties of the standard model as we went to high energies. Run 2, which started last year and is just about to restart again, that will start to look more closely for effects which may go beyond the standard model. And future accelerators are currently being considered in order to improve this precision. So here, just to illustrate that the LHC is a synchrotron, so what happens in the LHC is that radio frequency cavities, so the things down at the bottom here, are used to boost the particle energies from their injection energy, which is 450 GeV, up to 7 TeV, and then they're held in orbit for typically about 8 hours or so. So the typical thing that happens is for a day, you spend a day of collisions. You have to go through a series of accelerators, and then you hold things stationary, just waiting for these collisions to occur. And in order for those collisions to occur, you need to bring the positively charged protons round back in a loop, and that requires dipole magnets. And then you need to focus them, and that requires quadrupole magnets to focus them, for example, at the interaction points where you want the collisions to occur. So this is CERN's particle accelerator chain. So this has developed over 50 years. So the very earliest proton synchrotron, for example, came from 1959. So the idea is that you have a linear accelerator, and you accelerate protons from the linear accelerator first. You send those protons through a booster, then the proton synchrotron, then the superproton synchrotron, and finally from the superproton synchrotron into the Large Hadron Collider, where you bring things together in collision. So here are those protons being brought into collision, and pictures being taken every 25 nanoseconds of hopefully interesting events. So these are the pictures which are taken within the detectors. So, of course, that took an enormous amount to do, but in fact, it was quite rapid, the progress. So in 2003, the detector hall was empty, and by 2008, we were ready for collisions. So this is the development of the Atlas detector, all the component parts coming together, so that finally we were ready and waiting for the LHC when it came to the point of collisions. So the idea with the Atlas detector is it's a huge detector. It's 44 meters long, it's 22 meters high, it weighs 7,000 tons. And for example, the central tracker, which we worked on here, that alone has 6 million readout channels. So it's not just the fact that these things are happening very rapidly, it's also the fact that you have lots and lots of readout channels to be read out simultaneously. And of course, it's a huge thing. So this, just to set the size, is a man inside the Atlas toroid before the rest of the detector came together. And then the computing is also on a very large scale. So that we refer to as the grid. So the web was invented at CERN to meet the challenges that we had in the 90s. And the grid was a step beyond that. So that was about distributing the data as well. So it enables us to analyze all of the data that comes from the LHC. That's petabytes of data. So petabytes and hundreds of thousands of CPUs now, which are distributed around the world and used not just in particle physics, but in other areas as well. So here's a snapshot of data being sent to various locations around the world, centered on Europe, but going off to the US, for example, and off to Russia and so on. So we're all bound together in one group, all working together towards a common aim of discovering the Higgs boson, for example. So there's a huge amount of activity which was needed. So even this development itself took over 10 years to develop that computing infrastructure. And then finally, we were able to produce real events. So this is a picture of a real event in the Atlas detector, which is one that we know with very high probability is one due to the decay of a Higgs boson decaying into 2 Z0 particles, into 2 electrons and 2 muons. And from an historical perspective, of course, I'm sure Peter could talk fully about the whole theoretical development which was needed from back in the 50s through the 60s, and how the standard model emerged by the 70s. But essentially, the experimentalists take up the story in the 80s with the discovery of the W and Z. Then the LEP collider was built, and a tunnel was built for that. That was in 1989. And so that was the beginning of the R&D for the LHC experiments. And then it took about 20 years of the first investigations into what exactly should the LHC experiments look like to the discovery of the Higgs boson. So the final results on July 4th, 2012 were these remarkable pictures. So everyone was convinced. And there were lots of celebrations at that point. And it was a remarkable month for us because we produced one more technical paper that I was working on, which was produced on July 2nd. July 4th, there was the announcement of the actual discovery. So finally, we had enough statistics. And here you can see 6 sigma evidence just from the ATLAS experiment alone for something which deviates from a standard model which doesn't include the Higgs boson. So that's the idea here, that there's something which you find at 125 GeV or so, which deviates from a standard model without the Higgs boson. And essentially, that was a period of revolution, and we published these papers at the end of July. Now, the technical details of the analysis itself, it's very complex. All I want to say here is that essentially you spend all of your time trying to understand the backgrounds as carefully as you possibly can. That the whole game is to understand the backgrounds in as much detail as possible, such that then your signal can sit out. And here you can see, I'm sure you can all see, these red signals with, if you look very closely. So you can see how minute these things are against backgrounds, right, in various channels. And this was the sort of evidence we were using in 2012. And then Run 1 continued into 2013. So by 2013, people were pretty much convinced, because here's Higgs going to ZZ, the Higgs boson going to ZZ decays here. So that's this thing. And here's Higgs going to photon. And again, you can see a peak there. And this just illustrates how it took 3 years to accumulate this data. So if you look at these distributions in 3 different channels, you can see that there's no sign of a signal early on. You're waiting for the statistics to build up. So here in the space of 30 seconds or so, you can see how it took 3 years to accumulate all of the statistics, which finally gave you enough precision such that you could say, yes, we've discovered something at 125 GeV, which we believed was a Higgs boson. But then we can start to look a little bit at its properties. So that was what we did in the next year or so. So the idea was that we talked about these quantum numbers associated with all of the particles. So the Higgs boson itself has certain properties. So it has a spin of 0, and it has an intrinsic parity which is positive. And so you can test hypotheses associated with being 0 spin versus spin 2 or spin 1, or negative intrinsic parity or positive intrinsic parity. And all the tests that we did, not so convincingly, but reasonably convincingly in 2013, were such that it was all consistent with the Higgs boson having the correct quantum numbers. So this was the kind of level of precision that we had by 2013. You may or may not be convinced, but by that stage in 2013, most people were convinced. And we could measure with some precision from the LHC run data, we could measure the mass of this thing at 125 GeV in various different decay channels. And so it was sufficient for the Nobel Prize Committee to award its prize to Peter and to Francois Englert for the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles, and which recently was confirmed through the discovery of the predicted fundamental particle by the ATLAS and CMS experiments at CERN's Large Hadron Collider. So that was a momentous moment. So that's where we stand. That's the sort of pinnacle of our reach, if you like. And what we're doing now in Run 2 is, yes, we're looking with some increasing precision at the Higgs boson and trying to test its properties, because it may be that deviations from the standard model will first be revealed by looking more closely at the Higgs boson. but we're also looking to see if there are anomalies beyond the standard model in different areas. So there are lots of theoretical ideas, but here are a few. So new gauge bosons, so some heavier gauge bosons than the Zs and Ws, supersymmetry, which is quite popular, so I might talk about that a little bit more, resonances, technicolor, extra dimensions which are curled up tightly on themselves, black holes, which you may have heard something about, little Higgses, hidden valleys, a large variety of possible signals. So all of these things we go out and we test for in exactly the way as we try to test for the presence of the Higgs boson previously, using the same ideas. So just choosing one of these, we don't have time to go into all of them. So supersymmetry is the conventional method to try to fix the Higgs mass. And the idea is that for every fermion, there's a boson partner, and for every boson in the standard model, there's a fermion partner set up at some new higher scale. So for all the standard model particles up here on the left-hand side, there are corresponding SUSY particles. And that allows you to fix the electroweak scale, but it has some issues as well. So it's a conventional method to fix the Higgs mass. It sort of doubles the number of states in the model. These fermion and boson loops cancel as we evolve the forces and so on, so it helps to unify the forces. But it does introduce quite a lot of new parameters, and depending upon how you specify the model, then it can be as many as 105 new parameters which aren't specified, but you can get that down to 4 if you want. And then the nice thing is that if you conserve something, so this is one of those quantum numbers called R parity, then the lightest supersymmetric particle could be a dark matter candidate. So then you'd get missing energy signatures in your detector. So this would be a representation of a missing energy signature. And you would have to combine data from the LHC with the astroparticle physics data in order to find convincing evidence that you might observe here at the LHC is the same thing that you're seeing in terms of dark matter, which governs the galaxy rotations and so on. So how far have we got in that search? So we started in 2015, so we're sort of halfway through. We're just shut down at the moment. We'll restart in next month, and we've got fairly far on this. So I'm not expecting you to make notes of every single one of these lines, but the idea here is that, so in terms of supersymmetric, so I said there were 105 parameters in principle. So you have to construct models which are more or less well defined. So these are all the various possible models of supersymmetry, and it depends upon exactly what the mass hierarchy is of the supersymmetric particles as to exactly how these will manifest themselves in the detector. But we go to great lengths to develop these models, simulate them in simulations of the detector, and then we can test to see whether we actually observe these things. So that's what we do. The conclusion at the moment is that these are all null observations. So all of these lines represent limits. So these limits go up to, and the scale here is in tera electron volts. So this is 1,000 times the giga electron volts we were talking about before. And they're all in the region of 1. So the null observations allow you to say there are limits on these supersymmetric particles in various different manifestations of the order of 1 TeV. And then for these more exotic phenomena, things like contact interactions or extra dimensions or these heavier Ws and Zs, you can set limits on those. And again, we've not observed them, and we set limits of the order of 1 TeV for those. So that's the current status of those searches. And then for the Higgs boson, so you noticed last time that maybe you were or maybe you weren't convinced by the bumps which were seen then. Maybe by run 2 now you'd be a bit more convinced. So here, for example, from CMS is their Higgs to gamma-gamma signal, and here from Atlas is the Higgs to ZZ signal. So it's now reinforcing the idea that we really do have the Higgs boson in our hands, and we're trying to understand its properties. And we now have sufficient precision in terms of the Higgs mass that we can, looking at the relationship between the Higgs and the top mass and the W mass within the standard model, we can see whether all of these things are consistent. And, okay, you may say, unfortunately, all of these lines and so on, they all overlap. So what that tells you is that the standard model is successful in terms of describing all of the things that we see in terms of the masses and so on. But what we want to do next is to improve the measurements of these things, to test the standard model with more and more rigor, such that we might see breaking points in this. But already the fact that the Higgs mass, the top mass, and the Stockholm coupling constant are already known with quite high precision already tells us something about the nature of our vacuum in theoretical terms. So it tells us that this vacuum that we sit in is in a region which is so-called metastable. So don't worry, it's sufficiently stable for us on any timescales you can think of. But the idea is that the vacuum that we sit in within the Higgs field, it may be stable, it may be metastable, and according to our current thinking, with simply the standard model particles extrapolated all the way up to these huge, huge energies, then it appears that we're consistent with sitting on the edge of metastability. Now, there are all sorts of caveats to that no new things happen in physics terms across many orders of magnitude, which has never happened before. So, one should take this all with a pinch of salt. But it does tell you that you don't have to go to the very highest energies to see things which are slightly beyond you. So if you have improved precision of the more everyday things, you can get insight into what's happening at some higher energies. And here, just to show that, here we look at the coupling strength to different fermions and bosons of the Higgs boson, and they're all, so 0 would be no Higgs, so the combined result is at the bottom. 0 is no Higgs, but the data we find are consistent with 1, so that says it's the standard model Higgs. And the idea next is that we'll try to improve the precision with which we explore these things. So you can see here that the sort of precision that we have is not, you can see these lines are, at best we're getting up to 10% precision on these various decay modes. So the idea next is to study things at the LHC. We'll upgrade, so after run 2, we'll go into shutdown mode for another couple of years. Come 2019 or 2020 or so, we'll come back with a new upgraded LHC with 10 times the luminosity, so 10 times more protons colliding together. We'll upgrade our detectors so that they can sit in this huge high radiation environment, and we'll try to look at these various decay modes with increased precision. So this picture, for example, shows you how you can extrapolate from what we are currently envisaging to get at 300 inverse femtobarns to what we might get with the upgraded LHC with 3,000 inverse femtobarns. So it just illustrates the kind of precision we can reach. Beyond that, beyond the LHC, the next step may be a linear collider. So you might try to produce huge numbers of Higgs bosons, see how they decay, and that may reveal little chinks in the armor of the standard model. Beyond that as well, there are all sorts of other ideas about how we might take the field into the future. And of course, the idea with all of these things is that by looking at these decays of the Higgs boson, that they will be governed by possibly new particles which stand slightly beyond us, but are there in the vacuum and will alter the relative numbers that we see of each of these decays. And so there are all sorts of models which can be tested with some precision at these Higgs factories. So in conclusion on this part then, so the birth of a Higgs boson. I didn't reveal the full horror of the standard model, you'll be pleased to know. So this is the standard model as written down mathematically. It incorporates the Higgs boson in there, but But what we were interested in was just this part. So this is the Higgs potential that is used to create the Higgs boson. So we've discovered a Higgs boson as predicted over 50 years ago. So it's been a triumph for many theorists, experimentalists, and engineers who worked on the theory, accelerator, detectors, computing and analysis. Whether it is the standard model Higgs boson or a, say, supersymmetric version remains to be seen. So that's what we're going to do next. And then you might be thinking about, I left a lot of things open. So some of you might remember back an hour ago and remember that we were talking about the very large scale of things. There are lots of open puzzles, and we don't have the answers to those open puzzles still. So as we go the other way round, from the infinitesimal to the infinite, so my thought on this was that this would be the century of scalar boson discovery. So the Higgs field, the really interesting thing is that it's neither a matter nor a force. So we know about matter, we know that quite well, we can feel it. We know about forces pretty well, about how things interact with each other, but we don't really know what a scalar boson is, really. We've just got this one example of this in nature, and how that emerged, we don't really know. We know that inflation needs an inflaton, and that in most models is actually another scalar field, but we don't know what that might be. So some rapid period of inflation in the early stages of the universe. Dark energy is about 2/3 of our universe, at least in some models that we're now putting limits on through LHC data. Those are scalar fields, and these new searches we're working on just now. Dark matter is 1/4 of our universe. That could perhaps even be a scalar field in some models, so there are LHC searches for that. But the idea overall is that understanding these infinitesimal scalar fields as we go through this next century will change our view of the infinite universe. So as we approach these problems in this way, then we may get insight from one field into another. So overall, exciting years are ahead. Okay, thank you.
Thank you very much. That was a wonderful tour de force. We have time for some questions. If you'd like to ask a question, we would like you to use a microphone. So if you want to ask a question, raise a hand and I'll direct a microphone to you. Do you want to stay there or do you want to come?
Whichever.
So here, please.
Thank you. That was extremely interesting. I can't say I understood everything, being a lay person. However, since so much hinges on what a scalar field is, could you say a wee bit more about exactly what it is?
Well, just in front of you, you happen to have the...
Word with them when we're done, but as you put the talk together,
I don't think we do. I think really it's very different from the W and the Z boson in a sense. It's not a vector field. It's governed by different quantum numbers. It seems to have essentially the sort of null quantum numbers effectively. So it sets the level, if you like, within our... it's sort of the simplest possible particle you could think of, in fact, in some ways. It's what you start... In the textbooks, you usually start with these scalar fields with positive parity and so on, and then can construct from there. And then you actually find that in nature we see lots of other things with different quantum numbers. So, to me, I don't know. I know it's very simple, but sometimes the simplest things are actually the most difficult things to truly understand, and that's, I think, the point at which we're poised, in fact.
So the Higgs is the only scalar boson.
Fundamental particle. It's so... So the inspiration, perhaps, for this came from solid-state physics, and there are equivalent scalar fields, but they emerge from other interactions. So, but at the level, if you think that the Higgs boson is a fundamental scalar, it's the first thing that we've seen that is fundamental in that way. But it may or may not be fundamental. So as we probe further, we may find that actually the true nature of this Higgs field is something which is composite. There may be some, and then history has revealed to us that every time we look and we find something which is, we believe, the fundamental truth, we go beyond that and we find actually that emerged from another more basic property. And all of these things may be brought together in some other simpler way.
And am I right in thinking that the Higgs applies equally to the quantum and the classical realms of physics?
The boson itself as a particle is a quantum object, and you can as this thing, as we get to everyday, like it's there and available to us with, according to the Heisenberg uncertainty principle, for some diminishing amount of time because it's a massive thing, but it's not classical in the sense of our everyday matter, and if you'd like.
I was just wondering whether it would
Can we move
provide
the questioning on, please?
a grand unification theory.
I don't know if Peter wanted to answer that, because I'm sure you've got more interesting insights. Okay.
Questions from other members of the audience? Yes, again, in front. Thank you.
The Higgs boson, I assume, is a particle that has mass itself.
Yes, so that was the 125 GeV that we measured quite precisely.
So does the Higgs field give the particle its own mass?
Yes, in this, yeah.
And is that the only field that actually has that kind of recursive property in physics? So it's like a field that gives itself its own property.
So
if that makes any sense.
So you start from this. So there is no prediction of any of these masses, right? They are all put in by hand, right? And even in the Higgs, so what we might consider as everyday matter, everyday mass, are the fermions, and those, the way that works is that you trade off a coupling constant, a so-called Yukawa coupling constant, for a mass, and so you actually, you've not got any further into the problem, because but what the Higgs boson does do is it specifies how the W and the Z boson, how that electroweak symmetry breaking between the W and the Z boson and the photon, how that occurs is predicted through this Higgs mechanism.
I think probably what you're asking is, we understand that it's the Higgs boson, the Higgs field, that gives mass to particles. Is that what gives mass to the Higgs particle? That's what you were asking, yes. Conceptual question.
No, we don't know. So we think it's fundamental. It's just the thing that we would know as mass. In fact, 98% of mass is actually generated from the self-energy of the gluons and inside the proton and the neutron, and that's a completely different mechanism. So it's it's all rather hidden, right? It's not as simple as you might think. Maybe you weren't thinking that.
Are there further questions? I think we're stunned. Thank you very much. Can I call on Professor Christine Davis, the University of Glasgow, to give the vote of thanks?
So I'm sure you'd all like to join with me in thanking Tony very much for that comprehensive tour of the discovery of the Higgs boson and the implications for our understanding of the universe. And since nearly 5 years now, since the discovery of the Higgs boson was announced, and you could see from Tony's talk how much more detailed understanding we now have of the properties of the Higgs boson. And we're all looking forward very much to new discoveries that will come out of this run too at the Large Hadron Collider. You, I hope, got the impression from Tony's talk, I think you would have done, that Scottish physicists have played a big role in this whole field. Peter Higgs, with his original understanding of the fact that there should be a particle there to be discovered, but also Tony and his colleagues at Glasgow and Edinburgh, who've played such a key role in the experiments that found this particle. And I wanted to say something about Tony's specific contribution here, and he's worn several hats as this endeavour has proceeded. Back at the beginning, when the LHC was being built, Tony led the UK development of the UK part of this worldwide grid of computing. He told you something about that in his talk, but obviously, and as you could see from the plots he showed, it's an incredibly complex computational challenge to dig out the evidence for the existence of the Higgs boson out of all the debris that comes out in these collisions, and these huge numbers of events that you have to analyze in order to dig out the pictures that you're looking for. Once the data started to appear, then Tony led various analyses that improved the identification of the Higgs boson and understood how to combine different pieces of information to improve the statistical significance of the evidence that was coming out through the experiment. And then in this year, 2012, when the discovery was announced, Tony was actually the chair of the Atlas Publications Committee, and they were the people who had to put together the evidence in order to convince everyone that Atlas and also obviously their sister experiment, the CMS experiment, had really found the Higgs boson. So all of that, as you heard, has been a huge success, and we're now moving on to getting more and more detailed information about the Higgs, and at the same time boxing our standard model of particle physics into such a tight corner that we're all hoping that something new comes out. So we're looking forward to a new discovery, and in a few years' time you'll be able to come back and hear a talk about those new discoveries. But for now, let's thank Tony very much for his fantastic talk.